Hello everybody, Mr. Hasty here. Today we're going to start on section 11, which has to do with electromagnetic waves. Today we're going to talk about primarily what electromagnetic waves are. So let's start with the definition. Electromagnetic waves are waves made by vibrating electric charges. So we're going to get into a pretty in-depth discussion here about what that means. Now, just to give you guys an idea of what we're talking about when we talk about electromagnetic waves, the one that you guys are going to be most familiar with is light. So I'm going to talk about light in terms of electromagnetic waves a lot, but it's only one type of electromagnetic wave. It's only one part of what we call the electromagnetic spectrum, which we'll get into more into section 11.2. So how are electromagnetic waves made? Well, there's two key points we need to remember from our discussions of magnetism and electricity. And that's that a moving current, which means moving electrical energy, creates a magnetic field. And a moving magnetic field creates current. Now, the example we talked about mainly with these was machine-based. If you move, when you're using a motor, you use electrical current to create a magnetic field that then spins your motor. But if you use a generator, it's pretty much the exact opposite. You move something mechanically that moves a magnetic field, which then produces electrical current. So when you take an electron and you vibrate that electron, that's a moving electrical field, and you create a moving electrical field, which creates a magnetic field, which then creates an electrical field, and it just goes back and forth and back and forth. And the diagram usually looks like this. The diagram is 3D, and I'm not great at 3D, so bear with me. So our electric field will go up and down and up and down, and our magnetic field will fluctuate, and they usually have a magnetic field fluctuating left and right. So it'll come, excuse me for my drawing, left and right and left and right. So that doesn't look real great. So if you were looking at this head on, the magnetic field is going to be going, this is up, then down, but this is out, then in. And so it's hard to tell from this. Your book has a really good picture of it on page 340. So I went and found that drawing, and as you can see, the red represents the electric field and the blue represents the magnetic field. So as the electric field changes, the magnetic field also changes, and they change together, and that's why they're called electromagnetic waves. You can't have one without the other, and causing one causes the other. All right. So let's talk about some of the properties of electromagnetic waves. So the first thing I want to note is, unlike a lot of the waves we've talked about, these are not mechanical waves. If you remember what it means, they don't need a medium to travel through. So these waves can travel through empty space. So the things that we talk about traveling through space in terms of waves, like outer space, like light, gamma rays, radio waves, those things are all electromagnetic waves. Electricity and magnetism do not need a medium. So we'd say they have no medium. Now, that doesn't mean that they can't travel through a medium. It just means that they don't need a medium. So the speed of these is very, very fast, and it's somewhat fixed. The speed of all electromagnetic waves is 3 with 8 zeros meters per second. 300 million meters per second. Now that's the speed through a vacuum. A vacuum is something that's empty and has no matter in it. Pretty close to like what outer space would be. But when electromagnetic waves travel through medium, it does slow them down a bit. Electromagnetic waves traveling through air travel at 299 million. Traveling through water, it's 226 million. Traveling through glass is 200 million. And through something like diamond is 124 million. So it can get slowed down quite a bit, but it's still traveling incredibly, incredibly fast. So this is referred to because, again, the most common EM wave that we deal with is light. It's referred to as the speed of light. Now, in addition, these do have a wide range of frequencies and wavelengths, just like other types of waves. However, the frequencies, if you remember, frequencies are how many waves per second, can get really, really, really high. So we can be talking about things with frequencies around 750 waves per second, for instance, or 550 waves per second. We can also get much higher than that. In terms of wavelengths, these numbers can get really, really, really small. We're talking nanometers, right? And a nanometer is, to give you a perspective here, 1 nanometer is 1 times 10 to the negative 9 meters. So that means it would take, see, that's 9 zeros, 1 billion nanometers to make up 1 meter, which a meter is just like the meter sticks we use in class. Now, all matter contains some amount of electrons, which are electric moving particles. And so that means that all matter is capable of generating some kind of electromagnetic wave or electromagnetic radiation. Now we're going to move on to some of the uses and some of the properties of how it interacts in our world. So EM waves and matter. So EM waves, because all matter is made up of atoms and all atoms have electrons, and electrons are these teeny tiny little negatively charged particles, all electromagnetic waves interact with matter. And the most typical way we envision this is if the wave is a vibration and it hits matter, that's going to vibrate the matter and make it move more. As matter moves more, it has more kinetic energy. And the average kinetic energy of an object is its temperature. So if we have an EM wave striking matter, it's going to increase kinetic energy, which means we have increased temperature. This is why light heats things up. If you have a light shining on an object, or the sun's light shining on the earth, the electromagnetic waves travel through the empty space or through the room or wherever it is, and they vibrate the electrons and the particles in that matter, making them move more, meaning there's more kinetic energy, meaning there's a higher temperature. So when we talk about electromagnetic waves, there's some really interesting stuff in the physics of these, and that is that they behave both as waves and as particles. So the first thing is that Heinrich Hertz in 1887 kind of figured out some things about the electric properties that were a little bit different than other waves he had studied, particularly that the frequency of the wave mattered more than the amplitude in terms of energy. And that didn't kind of gel with what they knew about how waves worked based on sound waves and mechanical waves like ocean waves. It didn't really sit right. In 1905, Albert Einstein kind of figured out that light and electromagnetic waves have this behavior that they act as particles sometimes. And those particles are called photons. Photons are massless particles, which means they have no mass. They don't weigh anything in that regard. Massless particles of electromagnetic waves. And he observed that you can actually make light behave as if it has particles under certain conditions in certain experiments. We're going to talk about those next time. So up until this point, we'd always thought that they pretty much light behaved like waves. It does all the things waves do. It reflects. We know that because we can look at ourselves in a mirror. It diffracts. We know it diffracts because, remember, diffraction's bending around an object, and you can see if you have something light go through a very tiny hole, you can see the light spread out from that hole, so it bends and it refracts. If you put light through a prism, it changes direction and or splits into different colors like the rainbow. So it has all the wave properties that we know and love that we assume it should have, but then it also has certain behaviors that act like particles. And so based on this, they kind of have this what we call dual nature of light, or dual nature of electromagnetic waves. Electromagnetic phenomenon behave as waves and particles, and it's kind of unique to them. So that wraps up our discussion for today. Next time we'll be breaking down the electromagnetic spectrum and looking at different parts of it. So I hope to see you there.